So we will continue with chapter 5 review. So it's that document we have started to modify, chapter 5 review here. So I'm going to the bottom of it, the section on problem 6, which is going to be an overview of what stoichiometry is about. And stoichiometry is really a term that you only hear in chemistry, and this is about, counting the number of, counting elements or compounds and get the amount of another substance, that when it goes through a reaction or things like that. So it's all about having chemical reactions and then calculate amounts of a product or reactant. And so using the balanced version of the the skeletal chemical equation F. So I have to bring that here. Should have done that before, but so this one, F, right? F, yes. I'll take that. It's a combustion reaction where we have a compound made of carbon and hydrogen. So we have a compound made of carbon and hydrogen reacting with oxygen from the air. And so I guess, I don't know the physical state of this one, but let me add that this oxygen, which is a gas in the air that we breathe, and whenever you are burning something, it's reacting with oxygen in the air and making carbon dioxide and water. If what you are burning is made of carbon and hydrogen, you will automatically have carbon dioxide and water as the products. So this is part of something I really want you to learn in this course is combustion reactions. When you are burning something that contains carbon and hydrogen, it takes oxygen from the air. So it's going to be with the reactant side. And you're making carbon dioxide and water. So the first question is asking for the molar mass of C4H10. So whenever you need the molar mass, you need to think periodic table, right? The periodic table is where you will find the molar mass, and you will need to add the molar mass of carbon and hydrogen in this case. And let me share the periodic table briefly here. So here we have carbon, and you take the atomic mass of carbon here, the 12.01. So 12.01 is in units of grams per mole. It used to be atomic mass unit if you're talking about only one atom, but it's the same number for molar mass, and then the unit becomes grams per mole. So 1 mole of carbon is made of 12.01 grams of carbon. So we'll take that, multiply by 4, and then we'll take the hydrogen. 1.01 is its atomic mass here in grams per mole. So 1 mole of hydrogen atoms equals 1.01 gram. So let's go back here and do this calculation. So 12.01 gram times 4 carbons. I'm specifying here, this is from carbons, plus 1.01 grams times 10 hydrogens. And so you take that in your calculator. So 12.01 times 4 plus 1.01 times 10. And my calculator answer is 58.14, and it's grams per mole of, I have to specify what it is, C4H10. Let me make this as subscript and make that blue so we see it better. Okay, so that's the molar mass of C4H10. So it's in units of grams per mole. Another way to write this is that 1 mole of C4H10. Oh, it's equals 58.14 grams. So you can also write it like this, of C4H10, right? It's grams of C4H10. So writing the molar mass this way, shows you how you can use this as a conversion factor, because that's an equality, right? It relates the grams to the moles of a substance. So how many moles of water are formed from 6.5 moles of C4H10? And so when a problem is asking you for moles of another substance from a different substance, you have to have a chemical equation with it, right? Otherwise, there's no way you can do that. It only is making sense if you have a chemical equation and those two substances are part of the chemical equation. So, so H2O here is a product, and we make 10 moles of H2O when we have 2 moles of C4H10. That's how you want to read this chemical equation. It's like a recipe that gives you the proportions in which the reactant react, and that gives you the proportions of the product that are produced, right? So when you have so hold on. So the coefficients here, the green numbers here are called coefficients, and they are in units of moles or molecules, right? There's no grams in there. It's 2 moles of C4H10 will react with 13 moles of O2, oxygen gas, to make 8 moles of CO2 plus 10 moles of H2O, right? That's how you want to read it. Or you can change moles to molecules. But typically we talk in moles because we need so many molecules to, have a sample that is visible. So how many moles of H2O are formed from 6.5 moles of C4H10? So here, if you keep the procedure, the way to be organized when you approach problems, always want to identify what is given in the question. And here what is given is 6.5 moles of C4H10, right? That's what is given here. And from that, we want to find out the number of moles of H2O. So want moles of MOL of H2O. Yeah, so the abbreviation for moles is MOL. So be very careful to not write MOL for molecules. You need to show more in the case of molecules. So how many moles of H2O do we produce from those 6.5 moles of C4H10? And so we saw that this equation that is given is giving you the proportions in moles between C4H10 and H2O, and it says that 2 moles of C4H10, and we say equal, even though it's not really an equality, per se, but it's the equal can be read as will lead to or yields or produces 8 moles of H2O, right? And we get this from the chemical equation. Maybe I'll put them in red so to really emphasize where this is coming from. Oops, it's not 8, it's 10, sorry. 10 moles of H2O, right? We're focusing on the 2 molecules that are talked about in the question here, and it's C4H10 and H2O. So it's 2 moles of C4H10 gives 10 moles of H2O. And this is just one conversion. We only need one conversion factor here because we have already an equality that relates the moles of C4H10 and moles of H2O. So we can start our calculation. And we always start the calculation with the given amount. Always start with the given amount. So here 6.5. Let me make this properly. 4. This formatting takes time. 10. So start by 6.5 moles of C4H10. It's your given amount. It's in the numerator, right? Even though here it looks like in the middle, in between, it's in the numerator. You could have, I could have it, oops, I could have this here in something like that and show it's just a 1 there, right? It would be the same. So, okay. When you start with this moles of C4H10, so the conversion factor will be written such that the moles of C4H10 are cancelled. So when you take your equality, you want to take the statement that has the moles of C4H10 and put it in the denominator of your conversion factor, because this way you will cancel the starting unit of moles of C4H10. And I remember how I told you, and I think I said that in your exam comment, it's very important you label, not just say mole. It's not enough. You have to say moles of what, grams of what. It is very important when you do stoichiometry, because you will change from moles of something to moles of something else. So it's necessary to identify completely what you have. Otherwise, you will be lost. You will not know, because it will not be written there for you, and you will not know what comes next, because the information will not be written for you. So it's really helpful to be careful about writing everything, all the complete units, H, and that's H2. Oh, right. And so we see that the moles of C4H10 cancels this way, and we are left with just moles of H2O. So, sorry. So the unit will be moles of H2O. Now in the calculator, you do 6.5 times 10 divided by 2, and that's 32.5 moles of H2O, right? So does it make sense? The proportions are from 2 moles of C4H10, you get 10 moles of water, so which is like 5 times more of moles. So here 6.5, about 5 times more. So 6 times 5 is 30. So yes, this makes sense, right? And we need to pay attention to Sig Figs here. So that's the calculator answer, right? And so the proportions of 10 moles of water over 2 moles of C4H10 are exact, right? Those coefficients in equations are exact. So that means you only look at the given amount of 6.5, which is 2 Sig Figs. So you keep the 3. The 2, what comes after the 2 is a 5, so you need to round up to 3, and then the dot was there, so it just stays like that. Oh, became smaller. Moles of water. Oops, no. Oh. Ah. Sorry, it's did I write that outside? Moles of H2O. Okay. So that answers question B. So there's another question very similar, just to practice and get because there's no way to learn this than by practicing. So let's go over this new question. So how many moles of CO2 are formed from 6.5 moles of C4H10? So the given from the text here is again 6.5 moles of C4H10. Want. So what do we want? It is asking for moles of CO2 this time. So moles of CO2, right? So it's going to be very similar calculation, but with the other product, right? So we need to extract the mole-to-mole conversion factor from the equation, the chemical equation. And here we have moles of C4H10, and the chemical equation tells you that 2 moles of C4H10 react to make, and this time is the 8 moles of CO2. 8 moles of CO2. Ah, okay. Moles of CO2. Right, so we got this from the equation with the coefficients. 2 moles of C4H10 gives 8 moles of CO2. And so we are ready to do the calculation, because again, it's a simple mole-to-mole conversion. There is only the need for one conversion factor, and we already have it. We already have the relationship between moles of C4H10 and moles of CO2. So then you start your equation with the given amount of moles of C4H10. No, H. Multiply by the conversion factor. So again, the moles of C4H10 here are in the numerator. And so the conversion factor must be written such that we will cancel moles of C4H10. So the 2 moles of C4H10 will go in the bottom. And so I'll copy that and put this. And it's 2 moles of C4H10. That makes 8 moles of 8 moles of CO2. So 8 moles of CO2. Right, so this way with the moles of C4H10 cancel, and we're left with moles of CO2, which is what we want. So that's showing you that this is the correct setup. So units cancel properly, and now we do in the calculator 6.5 times 8 divided by 2, 26. So some people might be tempted to make the 8 and 2 like a 4 and a 1. I don't want you to do that, because then we are not sure where this is coming from. By keeping 8 moles of CO2 for 2 moles of C4H10, you really can see where this came from. It came from the coefficients of the chemical equation. So I want you to keep those numbers properly written and not, simplify. So we need to keep 2 Sig Figs. As earlier, the given amount is limiting to 2 Sig Figs, and we have already 2 Sig Figs there. And again, does it make sense? So from 2 moles of C4H10, we make 8 moles of CO2. So basically you multiply by 4. And so 4 times 6.5, 4 times 6, 24. And so 26 makes sense here, right? So a new question now. These were just what we call mole-to-mole conversions, right? Mole, changing a mole of a substance to the mole of another substance using a chemical equation. Now, the question is asking for how many grams of CO2 are formed from 145 grams of C4H10. So this time we are dealing with grams. And we know that our recipe here, our chemical equation is in units of moles. So you will not be able to change grams of a substance to grams of another with just one conversion factor. To change from one substance to another, you have to do it in units of moles because these coefficients are in units of moles. So that tells you you will need to convert your grams, the given grams here of 145 grams of C4H10. You will have to convert them in moles of C4H10. And that's where the molar mass is handy here. So let me copy that. We'll need that for sure because the given, so let's say here the given is 145 grams of C4H10, right? Because this is the given and it's asking for grams, so question mark grams of CO2, right? Grams of CO2 that are made from those grams of C4H10, which I think is butane, would be easier to say than C4H10. So we have grams of a substance and we want grams of another, and so we will need to go through moles. And so maybe I should show the roadmap here. I think it is helpful to have a roadmap to show you if what you need to do and when you're doing it to see if you're done or not. So we start with grams of, and here it's important to have, and let's make it shorter by doing just this. Oh, C4H10. Okay, I have to keep doing that subscript thing. Oh. H10. Okay, so we have grams of C4H10. That's the unit of the given, right? And we will need to change that to moles of C4H10. And for this, you use the molar mass of C4H10. So change the grams into moles. And then once you have the moles, that's when you are able to change that to moles of CO2. CO. Using the coefficients from the equation. And then, because the question is asking for grams, then we can go back to grams of CO2 using the molar mass of CO2. So that tells you you will also need the molar mass of CO2, right, for that last step. So these roadmaps here are showing you the amounts, the units of the amounts you start with, intermediate answers, and then the unit of the amount of what you're looking for. And so the arrows, where you have the arrows, it tells you you need a conversion factor there. And there is 3 arrows, which means we will need 3 conversion factors. And we already have an equality here, this one that tells you how to convert moles of C4H10 to grams of C4H10, and that will be useful for the first conversion here. We said for the last one, the moles of CO2 to grams of CO2, we will need the molar mass of CO2. Oops, what did I do? Close. This is not super subscript, so moles of CO2 equals. So I don't think you need to see the periodic table here, but so you take 1 time the molar mass of carbon, and it's 12.01, plus 2 times the molar mass of oxygen, and it's 16 times 2, 16.00, and so the molar mass is 44.01 grams of CO2, right? So that's the molar mass of CO2, and that will be useful for the last conversion. And so in between, we have another conversion that is needed here. And this conversion will change the moles of butane to moles of CO2. And that is found in the chemical equation there. So it's moles of butane to moles of CO2. So we will use the 2 moles of C4H10 equals, or gives 8 moles of CO2. And we actually have it here, so let me copy that. So 2 moles. Formatting is kind of weird. Okay, 2 moles of C4H10 equals 8 moles of CO2. So we have our 3 equalities that we can use as conversion factors to do this conversion here. So we can start writing our setup. And so always start with the given amount. So here 145 grams of, let me copy C4H10 from here. C4H10. Let's have this. Okay, so that's our given amount. And you always multiply, and we will multiply by 3 conversion factors, we said. Yeah, I need to multiply in between. Oh, okay, to redo that properly. So times another conversion factor, times another conversion factor. So we will have 3 of them because we have 2 intermediate units. So you start with the given amount of 145 grams of C4H10, and you want to change that to moles of C4H10 according to the roadmap here, and use the molar mass of C4H10. And you want to cancel the given unit of grams of C4H10, so you will put those grams of C4H10 here in the bottom so that you can cancel the unit. Let me change that so that it's properly formatted, right? Again, as I said, it's important that you write the units fully. It's not just grams, it's grams of butane, right? And that's 58.44 grams for 1 mole. So 1 mole of C4H10. Let me make this whole thing like that. Okay. So if you were to stop here and calculate, you would get the moles of C4H10 that there is in 145 grams of C4H10. But we don't want to stop here. We are not interested in that value. We want to keep going and change the moles of C4H10 into moles of CO2, right? So we'll do the second conversion, and for this we need to change the moles of C4H10 into moles of CO2 and cancel the moles of C4H10 in the previous conversion factor, right? Those moles of C4H10, we want to cancel that unit. So in the next conversion factor, you want moles of C4H10 there, right? And the conversion factor between moles of C4H10 and moles of CO2 here says it's 2 moles of C4H10 for 8 moles of CO2, right? So let's put 8 moles of CO2 on top. Oops, no, okay. Oh, no. Um, hmm. um, uh, okay. So I just wanted that as a subscript. Sorry, it's a bit annoying to have to do all of that each time, but okay. And this is C4H10. It's important you write that so that you can see why you can cancel moles of C4H10, right? Between here and there, right? They cancel out. And so you're left with moles of CO2 at that step. You know, the intermediate unit, if you were to calculate, would be moles of CO2. But that's not what we're interested in. We want grams. So we need to continue and write the last conversion factor that will change the moles of CO2 into grams. And we want to cancel moles of CO2, you know, that is in the previous conversion factor. So we will want the 1 mole of CO2 in there, in the denominator. My headset is sliding backward, and I hope you hear me well. And that's 44.01 grams of CO2. Okay, so I cannot really show how the units cancel with, you know, lines that, you know, cross the units, but I really want you to emphasize that grams of C4H10 here cancel with these ones. Then moles of C4H10 cancel with these. Moles of CO2 cancel with that. And so we are left with grams of CO2. So that will be the final unit because that's what is left as far as units. So in the calculator, you do 145. So I advise to multiply all numerators together and then divide by each denominator. There's other ways to do this. You can also multiply by the numerators together and then divide, open the parentheses, and then multiply the denominators together. To avoid using parentheses, I just multiply all the numerators together. So 145 times 8 times 44.01, that's all the numerators, divided by 58.14, divided again, so be careful when you don't use parentheses, divide again by 2, that's the denominator, and that's it. The 1 is not necessary to do, so equal. And so my calculator answer is 439.04. So I'll stop there because I know it's going to be plenty of Sig Figs. So let's look at Sig Figs. Whenever you have 1 mole of something, you know, or 8 moles, 2 moles from the coefficients, these are all exact numbers. So these are exact number, this, and that. What is not exact are molar masses, but they have 4 Sig Figs, both of them 4 Sig Figs. And so what is limiting is the given amount, and typically that's what it comes down to. The given amount is the limiting amount in number of Sig Figs. That's 3 Sig Figs there, so we need to keep 3 Sig Figs. So let's make it 4, 3, 9. And what comes after the 9 is a 0, so you keep the 9 and you drop everything. And the 9 was where there was the decimal point, so we keep it like this. Grams of CO2. Right, and please write the units of what you are calculating in the end fully. It's not just grams, it's grams of CO2 that are formed from 145 grams of C4H10. So that's how I want you to do this kind of problems. And if you show all of that, it's really great. It's the best. so, so, so question E, how many grams of CO2 are formed from 225 grams of O2? So very similar question as earlier, because it's asking for grams of CO2, but this time from grams of oxygen. So what changes is the given amount. It's not butane anymore, it's the oxygen, right? Oxygen is part of the reactant. So let's do a given. Let me make this. So given is 225 grams of O2. So O2, it's an element and a molecule at the same time, right? It's one of those diatomic molecules that you find as gases, an diatomic molecule, O2, like H2, N2, Cl2, F2, Br2, I2. There are 7 of them like that. What do we want? The question is asking for how many grams of CO2, right? So grams of CO2 that are made when you are burning 225 grams of oxygen. So again, it's a gram to gram conversion, and it's grams of something to grams of something else. And you know, you cannot change that without having a chemical equation given. And here the chemical equation is telling you here 2 moles of butane will react with 13 moles of oxygen to make 8 moles of water and 10 moles of 8 moles of CO2 and 10 moles of water. So this is what relates oxygen to carbon dioxide in our case. And it says we have 13 moles of O2 making 8 moles of CO2, right? So we know we will use that. So it's 13 moles of O2 are making 8 moles of CO2. And so you can convert them from one to the other, but it will be in units of moles. And we are given grams. So that tells us we will need first to change those grams of oxygen, 2 moles of oxygen, to be able to use this equality. So we need the molar mass of oxygen, because what relates grams to moles of a substance is the molar mass. And you get the molar mass from the periodic table, right? Periodic table here. Oxygen. So be careful when you do the molar mass of oxygen. It's the molecule of oxygen O2. It's made of 2 oxygen atoms. So it's not just 16 grams, it's 16 grams times 2, because there is the subscript 2 that tells you 2 oxygen per oxygen molecule. Right? We call them the same way. We say oxygen for oxygen atom, and we say oxygen for O2. I know this can be confusing. In the periodic table, it shows you the atom, but when you're dealing with the oxygen in the air, it's the molecule O2. Let me go back here. So it's going to be 1 mole of O2 is 32.00 grams of O2. Right? So oxygen, we say oxygen, but it's O2. It's 2 atoms of oxygen making a diatomic molecule. And so we need the molar mass of oxygen to change the grams of oxygen to moles of oxygen. Then we will use the 13 moles of oxygen gives 8 moles of CO2 to change the moles of oxygen to moles of CO2. And then the question is asking for grams of CO2. So after that, we will need to change the moles of CO2 into grams of CO2. And we already have the molar mass above here. It's this 44.01 grams, right? So let's show the roadmap to, put this more clearly. I think it's good to have a roadmap. So we start with grams of O2. Grams of O2. We change that to moles of O2. This is annoying. The O2. Okay. Then once we have our moles of O2, we can change them to moles of CO2 using this. So moles of CO2. Oh, I'm out now. CO. Oh. Oh, this formatting is really taking a lot of time. Sorry. And then so once we have moles of CO2, we will go back to grams of CO2. Right? So that's our roadmap, right? The roadmap shows you the unit you will go through. The arrows again are showing you will need the 3 conversion factors, 1 conversion factor for each arrow. An arrow symbolizes a conversion. So a conversion from grams of oxygen to moles of oxygen. And for this, you will use the molar mass of oxygen that says 1 mole of O2. And I'll put it first because we will use it first. 1 mole of O2 is 32 grams of O2. That will allow us to change grams of O2 to moles of O2. Then we can change the moles of oxygen to moles of carbon dioxide using this conversion we got from the coefficient of the chemical equation. And once we have our moles of CO2, we can change them to grams of CO2 using the molar mass of CO2. That's going to be the 3rd step. So let's start the calculation. I'm still in there. Or what's... okay. Okay, so we start with 225 grams of O2. O2. And then you multiply your given amount. So that's the given amount, 225 grams of O2. And you will multiply by the first conversion factor, which change the grams of O2 to moles of O2. And to know which way you write it, so it's the molar mass of oxygen, right, that you're using, because that's what relates moles to grams of oxygen. And you see that you start with grams of oxygen, so you want to place the 32 grams of oxygen on the bottom so that you will cancel units. of grams of O2. Ah. Oh no. Mm. Sorry, I have a bit of a hard time with formatting today. O2 here. Remove that. And that. Okay. For 1 mole of O2. I have to write it. It works better. Okay. So we've used the molar mass here as a conversion factor to change grams of O2 to moles of O2. At that point, you have moles of O2 and you want to change them to moles of CO2. So the next conversion factor will use the fact that 13 moles of O2 equals 8 moles of CO2. And you want to place the 13 moles of O2 in the denominator because you want to be able to cancel moles of O2, the units of moles of O2. Ah, why is it gone each time? Uh, okay. And on top it's 8 moles of CO2. So here moles of O2 cancel, right? And you're left with moles of CO2. So the next conversion factor will have to cancel those moles of CO2 because that's not the unit you want in the end. So the next conversion factor has to have moles of CO2 on the bottom here. And you need to change the moles of CO2 into grams of CO2. So you will use the molar mass of CO2 and place the 1 mole of CO2 on the bottom. And 44.01 grams of CO2 on top, right? And we see that our setup is correct because we cancel grams of O2 with grams of O2 here, moles of O2 with moles of O2 there, and moles of CO2 with moles of CO2 here. And we are left with grams of CO2, which is what we want, right? So it works. We have the desired unit at the end. The other units have all cancelled. And then on the calculator, you do 225. So I like to multiply all numerators together. So times 8 times 44.01. And then divide by each denominator. So divided by 32.00. Divided again by 13. And equal. We don't need to divide by 1. So the calculator answer is that. And there's more digits, but that's enough here. We can cover the number of Sig Figs. So again, 1 moles of CO2, 8 moles of CO2 over 13 moles of O2, all of these are exact numbers. Here in the molar mass, we have 4 Sig Figs. There we have 4 Sig Figs. And so it's the given amount here that has 3 Sig Figs, and that is limiting the number of Sig Figs. So 3 Sig Figs. So we keep the 1, the 9, oops, and the 0. What comes after the 0 is a 4, which means we round down, and we keep the 0, and we drop the 42. So notice how I keep the dot, and that's on purpose because I want 3 Sig Figs. And if I didn't show the dot, it would be 2 Sig Figs. Now that I show the dot, the decimal point, it makes it 3 Sig Figs. So you have to keep it here. And yeah, I guess I could have rewritten this to show the 190 CO2. It's grams of CO2. Okay, so that's the amount you would get from burning 225 grams of oxygen, according to that chemical equation. Let's continue with question F. Which reactant is the limiting reactant? Is it 145 grams of C4H10 or is it 225 grams of O2? Let's say you are doing the reaction and that's what is available. You have 145 grams of C2H10 and 225 grams of oxygen. And so you want to know which one is the limiting reactant. And so normally you would not have done the calculations before that. And the question is asking what is the theoretical amount or theoretical yield of CO2 produced? Let me just remind, let me copy that here. Just because it's nice to have that under our eyes. So if we have 145 grams of C4H10 here, and if we have 225 grams of oxygen, you know, which one will allow you, will limit the amount of CO2 produced? That's what the question is asking. Which one is the limiting reactant, which means which one will limit the amount of CO2, because here we were asking for CO2, grams of CO2. So which one will limit the amount of CO2 that you can produce? And so when you have that kind of question, what you would normally do is take your 145 grams and calculate the amount of CO2 that you would produce from that. And so that's exactly what we did here. We took 145 grams of butane and changed them into CO2 because we are interested into how much CO2 we can produce. And so that's the amount of CO2 that 145 grams of C4H10 would produce, right? If you have enough of everything else, right? According to the reaction, if you had more than enough of oxygen, this amount of C4H10 would produce that amount of CO2. And that's what is called the theoretical yield, if you will, for 145 grams of C4H10. Theoretically, that's what you would produce if you had enough of everything else. And the theoretical yield of 225 grams of oxygen is the one we calculated here. From 225 grams of oxygen, if you had enough of everything else, and then we calculated that we would get 190 grams of CO2, right? That's what, you know, those are theoretical calculations. We take the proportions and we hope that, you know, they really can perform 100% and produce this amount of CO2. So you see that one amount versus the other, you know, there's a big difference. From 225 grams of oxygen, you can produce only 190 grams of CO2 versus 430 grams of CO2 from 145 grams of C4H10. So that tells you that the amount of oxygen available here, 225 grams, will limit the amount of CO2 produced to 190 grams of CO2, because out of these grams of oxygen, you cannot make more. That's what the calculation shows. You can only produce that. So even though you have the possibility to do more CO2 from those 145 grams of C4H10, if you have no more oxygen available, you will not be able to make them. So the limiting amount then is oxygen here, is the 225 grams of oxygen, because from that you can only produce 190 grams of CO2. So let me write this. So the limiting reactant is, I will write it like that, but it means O2, right? Is oxygen, well, let me make sure, O2. So the limiting reactant is oxygen because 225 grams of oxygen can only produce 190 grams of CO2. Oh, where is this? Oh, it's because of the dot. No. So the limiting reactant is oxygen because 225 grams of oxygen can only produce 190 grams of CO2. You know, it is the smaller amount of product between 439 grams and 190 grams of CO2 that would be produced. Well, actually, it's the 145 first, 145 grams of. Okay, so good. I'm glad it's helpful because it's sometimes difficult to grasp that concept at first. So the limiting reactant is the one that limits the amount of product you can make, and so you calculate what you would get from both amounts that are given. And the one that gives the smaller amount of product will be what you can produce from those, from the amounts that would be available initially, right? So that's why it's called like that, limiting reactant. It's completely used up. So by having 225 grams of oxygen versus 145 grams of butane, the whole grams of oxygen will be used, and you will produce a maximum of 190 grams of CO2, and you will have some leftover of C4H10. There will be some leftover, right? Because from that you would have been able to do much more, but there's not enough oxygen available. So we say that C4H10, C4H10, let me take that. C4H10 is the reactant in excess. We say that it's the reactant in excess because there will be some leftover. Oh, it's that big. Okay, is the reactant in excess, and there will be some left over. While O2 will be all consumed. Okay, so then the question is asking what is the theoretical amount of CO2 produced. So we already calculated that in the previous two questions. And so the theoretical amount of CO2 produced will be 190 grams of CO2. This is what theoretically you should get if everything else is plentiful, and you calculate it given the proportions given by the equation. That's what you should get, right? So, but if the amount of CO2 produced from 145 grams of C4H10 and 225 grams of O2 is this 151 grams, so what is the percent yield? So for this, the percent yield, there is a formula. So let me go to the reference information for that. So you go to your reference packet, and let me emphasize here that page 1 is not dealing with chapter 5. The page 2 is, and what's on top here is for chapter 10, which we will not cover. But here, the bottom of page 2, right? Page 2 here. The bottom of page 2 has the information you need for anything dealing with chapter 5. So the Avogadro number, those conversion roadmaps. And so be careful, the conversion roadmap, the first one here is for changing particles of a substance to moles of a substance, but the same substance, of course, and to grams of that same substance. So it's when you're dealing with just one substance and you want to know, how many grams you have from a given amount of moles or a given amount of particles. Or vice versa, you could have grams of that substance A, you want to convert it to a number of moles or particles. So it says you need the Avogadro number between particles and moles, and you will need the molar mass when you are converting between moles and grams. So what we did today, stoichiometry corresponds more to this type of roadmap where you are dealing with different substances that are related together in a balanced equation. So like, for example, W here is a coefficient, WA plus XD, so X is the coefficient, D is the reactant formula. Give YB, so B is a product, plus Z C, and C is another product. So you have to have a chemical equation when you're using this roadmap, because you're changing moles of A to moles of B, for example, here. When you are doing this, you need the equation coefficient given with the equation. And if it's not moles but grams that are given, then you need first to change the grams of A to moles of A using the molar mass of A. And then you can change the moles of A to moles of B. And if the question was asking for grams of B, then you need to continue and change the moles of B to grams of B using the molar mass of B. And so there is an example of what a calculation would look like if you change reactant grams into product grams. And this is what we did today. We started with reactants like butane and oxygen. We used the molar mass of the reactant to change that to moles. Then we used the coefficient to change the moles of butane to CO2. And then we use the molar mass of CO2 here to get back to grams of CO2. So it's another way to help you know how to write those calculations. But here, we were here for the percentage yield. So the formula is that the percentage yield is the actual yield over the theoretical yield times 100. I cannot copy that. So let's remember this: actual yield over theoretical yield times 100. So percent yield is equal to, and I'd better use the equation here. It's, oops, why does it go away? Okay, we said it's actual yield over theoretical yield, theoretical. Is it written like this? I'm not sure. Hold on. No, it's a E. Times 100. Don't forget to multiply by times 100, and it will be a percentage, right? Equals. So that's the formula. Let me make it blue so we see that. And so the theoretical yield, we just answered the question above. What is the theoretical yield? Oh, what is that value? The theoretical amount of CO2 produced from those amounts of reactant was this, right? So this is our theoretical yield here. So let's make this red so we really see that. And then the actual yield is what the question is telling you here. If the amount of CO2 produced from 145 grams of C4H10 and 225 grams of O2 is 151 grams. So that's the actual yield. So let's just plug in the values and we will have the actual yield is 151 grams. And here we are talking about CO2, CO2. And it's 190 on the bottom for the theoretical yield, CO2. Times 100 equals, so you do on the calculator 151 divided by 190 times 100. And it's 79.4736. I'm giving more than needed because that's the calculator answer. Let's think about Sig Figs here. The 100, whenever you calculate a percentage, the 100 will always be exact. So we only are looking for the actual yield and theoretical yield, and which is 3 Sig Figs. So we keep this. Oh, whoops. 190 here. We're here. And we keep the 7, the 9.4. That's 3 Sig Figs. What comes after the 4 is a 7, so you need to round your 4 to a 5 and stop there. You know, drop everything after that, and that's a percentage. So that would be the percent yield of CO2 that you would get, because 151 gram is less than the theoretical amount, and that's typically what happens, right? It's rare that your reactions work 100% and give you exactly the amount you were expecting. In reality, the reactions don't always are complete, and there can be losses. So that's why it's rare to have 100% yield. So here, 79.5. It's not too bad, but it could be better depending on if this is important or not to have a good yield. Oh, and that's the end. Okay, so